Okay, so good morning. Today I will be talking about unveiling the CP or Higgs in a generalized 2HDM at a muon collider. So this is based on this talk is based on this archive paper with Nivedita, a PhD student from ISCS Kolkata. This is the brief outline of my talk. Coming to the motivation, we all know that muon G-2 anomaly has been one of the long-standing motivations for the particle physicists to look for BSM scenarios. And from muon G-2 collaboration at Fermi National Laboratory, along with the old BNL data, shows a 5.1 sigma deviation from the standard model prediction. Although there are many models and theories to address this issue, the enhanced coupling of the muon with the non-standard BSM particles, which is necessary to explain muon anomaly in general, has not been extensively probed in colliders yet. And also this coupling can be directly probed in the futuristic muon collider. So in our work, we have considered to explore such a muon-philic scenario. Before going into detail to the model part, let me briefly talk about some novelties of the muon collider. So first of all, compared to a hadronic collider, muon collider can provide the full energy uses, as in the hadron colliders only a fraction of energy can be used. Secondly, it is very clean because there is no hadronic activity present. And thirdly, compared to a E plus E minus collider, due to relatively low synchrotron radiation, muon collider can achieve a very high energy muon beam. So considering all these effects, one can safely say that muon collider will be a very elegant choice for the upcoming ages, which can provide the advantage of both PP and E plus E minus colliders and offering the benefits of high energy and high precision. Also, since it's a very early stage of proposal, it's proposed to run at 1 autoburn inverse luminosity for 3 TeV and an upgradation of 10 autoburn inverse luminosity for 10 TeV. So, even for high luminosity LHC, the luminosity is proposed to be 1 autoburn inverse, which will be equal to the 3 TeV machine, and we hope that new physics could be discovered at muon collider at its early stage. So coming to the model part, we have considered a generalized 2HDM with a minimally perturbed type X sector. This is the lepton specific one, and one can write the most general potential, and after electric symmetry breaking, we can expand the neutral thing, and the ratio of the wave is defined as tan beta, which is a key parameter of this model. And we can get the charged scalar, physical charge scalars and the CP odd scalar by changing from this gauge basis to the mass basis with this transformation. And similarly, for the CP even sector, by this mixing angle alpha, we can get the physical Higgses. Now, one should know here that out of these two Higgses, anyone can be the SM-like. And in our work, we have considered the higher CP event to be the SM-like. Now, in absence of any Z2 symmetry, this is the Yukawa Lagrangian, and one can see that there are these Y1 and Y2 Yukawa matrices, and we cannot simultaneously diagonalize them. And by this reference, we have taken from this reference where we choose to diagonalize Y2U, the up, down and the lepton sector coupling, and the others remain non-diagonal, giving rise to the tree level FCNZ. So this is the Yukawa Lagrangian for the neutral scalar, and where M's are the diagonal matrices and sigmas are the non-diagonal matrices. And we parameterize it in terms of chi's, and we have chosen this to be symmetric for simplicity. And for this 3 generation of leptons, these couplings will be noted by y e mu, y tau mu, and y tau e. Okay. So coming to the muon anomaly, we all know that the gyromagnetic ratio of muon is 2 at tree level. However, it suffers from loop correction, and in the standard model it deviates from 2, and the mu is defined by g minus 2 by 2, which takes this value. However, from this FNAL measurement with old FNL and BNL gives this number, which is clearly 5.1 sigma away from the standard model prediction. Now one can argue that there is results from lattice QCD by this BMW collaboration, and also from E plus E minus to pi plus pi minus from the CMD3 experiment. However, since there is no firm confirmation, we choose to work in a paradigm where this 5.1 sigma exists and new physics contribution is needed. So we scan our parameter space and we calculate muon anomaly in both one loop and two loop Barzi diagrams we have taken into account, and this is the parameter space in M8 and beta plane, and we see from here that low mass and higher tan beta are preferred to satisfy muon anomaly. Now one should be careful here that the diagrams that contribute to the muon anomaly, similar diagrams will also contribute to the lepton flavor violating processes. And as we know that there is no excess in these processes, so there are constraints on these branchings. So the strongest bound comes from Meg experiment mu2 E gamma, and we have seen that to satisfy both this LFV and muon anomaly, one needs to put these lepton flavor violating couplings to be order of 10 to the power minus 4 or lesser. Now coming to the constant of the model parameter, we have taken vacuum stability and perturbative unitarity. So first of all, this is the set of equation needed for vacuum stability. Also for unitarity, one needs the lambdas to be less than equal to 4 pi, and to have lambda 1 to be less than 4 pi, this one should ensure this constant is satisfied. Also the presence of the non-standard Higgs will change the electric constants, and we have taken into account all these STU parameters to be within 2 sigma allowed range. Third is the B physics constraints. Since there are these non-zero efficiency Yukawa matrices, B2 S gamma and the others will be modified, and we can evade this by taking the charged Higgs mass to be greater than 150 GeV and the couplings properly. The final important one is the constant from collider. So there are many constraints. Due to shortage of time, I will not be able to go through all. So the most stringent condition that constraints our model parameter is this 125 GeV Higgs decaying to the pair of light pseudoscalar. Since our pseudoscalars are less than mH by 2, this constraint is very important, and we have explicitly checked that by proper tuning of this tan beta M12 square and M1H, we can keep this coupling near to 0 by and satisfy this constraint easily. So I would conclude this section with the remark that our choice of parameter is the lower CP even Higgs is 110 GeV, higher CP even Higgs is 125 GeV, charged Higgs is 165 GeV, and we have varied the pseudoscalar mass from 30 to 50 GeV and tan beta from 50 to 80 GeV for our collider analysis. Okay, so in our work we have explored this channel mu plus mu minus to monophoton plus CP out scalar, where CP out scalar goes to tau plus tau minus, and tau are followed by the leptonic decays. So this is the leading diagram, and this is the choice of benchmark, and you can see the production cross section varies from 0.43 femtobarn to 0.78 for all these 4 choice of benchmarks. And the standard model processes that mimic these signals are gamma VV and gamma tau tau, and we have written the model file in fine rules and passed it to MATGRAPH Pythia, and the Delphis card we have used is the Muon collider Delphis card that is embedded in this Delphis. And along with these pre-selection cards, we have defined few other kinematic variables and put cards on that to maximize the signal significance. So first of all is the PT of this leading lepton, and for the signal case, since it comes from the low mass pseudoscalar, it tends to peak at the lower side, and the other one is the pseudo rapidity. For the signal, it's near to the beam axis, so we have put a mod of eta greater than 1 or 1.5 depending upon the benchmark choice. Third is the PT of this photon. For signal, it comes directly from mu plus mu minus, so it peaks at the higher side. Similar distribution for eta as eta of gamma as eta of L, and delta for this signal are coming from the 2 taus, so they are peaking at the smaller size, and also the missingnity that is coming from the neutrinos. So we haven't put any card, just we have choose missingnity to be greater than 10 for both signal and background. And with this simple card based analysis, we see that for all the 4 benchmarks we can get we can probe all these 4 benchmarks with significance greater than equal to 4 sigma at 1/1 inverse luminosity. Just to compare with the HL-LHC, even at the cross section level, there is a suppression of 200 to 800 factor. This is due to the fact this pseudoscalar lepton-lepton coupling is proportional to tan beta, and this pseudoscalar quark-quark coupling is proportional to chord beta. Since for Muon anomaly, satisfying Muon anomaly, we need higher tan beta, so this coupling for the leptons are enhanced and reduced for this quarks. So I will conclude here. So we have investigated the prospect of probing the light pseudoscalar at 3 TeV Muon collider, and we have also satisfied all the theoretical and experimental constraints, and we have searched for this signal, and yeah, for 30 to 50 GeV can be probed with significance greater than or equal to 4 sigma, and also as we don't know the luminosity reach of the Muon collider, we can hope that more parameter space will be probed if it's built. So thank you.
Thank you, Nivedita di.
I have just one comment. So it's officially my last working day here. So I would like to thank all the faculties and all the staffs and fellow students.
Thank you.